Hi friends, in this session we consider a function called isomorphism that helps us to examine whether two algebraic systems are alike or not. Groups are binary structures and hence we discuss whether two groups are isomorphic or not. Isomorphism between binary algebraic structures. Definition: let S star and S dash star dash be binary algebraic structures. An isomorphism of S with S dash is a one-to-one function phi mapping S onto S dash such that phi of x star y is equal to phi of x star dash phi of y for all xy belong to S. Property 1. If such a map phi exists, then S and S dash are isomorphic binary structures, which we denote as follows. Property 1 is called homomorphism property. Remark: in property 1 considered above, the product x star y on the left hand side takes place in S, while the product phi of x star dash phi of y on the right hand side takes place in S dash. Procedure to verify whether two binary structures are isomorphic. The procedure to show that two binary structures S star and S dash star dash are isomorphic is as follows. Step 1. Define the function phi that gives the isomorphism of S with S dash. Now, this means that one has to describe in some fashion what phi of S is to be in S dash for every S in S. Choosing the function phi is very important. Step 2. Show that phi is a one-to-one function. That is, to show that phi of x is equal to phi of y in S dash implies x is equal to y in S. Step 3. Show that phi is onto. That is, to show that corresponding to each S dash in S dash, there exists a S in S such that phi of S is equal to S dash. Step 4. Verifying the homomorphism property. That is, to show that phi of x star y is equal to phi of x star dash phi of y for all xy belongs to S. This is just a question of computation. One computes both sides of the equation and see whether they are the same. We now consider some examples of algebraic structures that are alike. Example 1. Show that the binary structures R plus and R plus dot are isomorphic, where plus is the usual addition and dot is the usual multiplication of real numbers. Solution. Step 1. Defining a function that will be an isomorphism. Define phi from R to R plus by phi of x is equal to e raised to x for x in R. Step 2. Verifying that phi is one-to-one. Recall that exponential function e raised to x is a function from R onto R plus and the logarithmic function ln x is a function from R plus onto R, and they are inverses of each other. That is, e raised to ln x is equal to x and ln e raised to x is equal to x. Hence, if phi of x is equal to phi of y, then e raised to x is equal to e raised to y. Taking the natural logarithm, we see that x is equal to y, showing that phi is one-to-one. Step 3. Verifying that phi is on to R plus. Corresponding to R belongs to R plus, there exists ln R belongs to R such that phi of ln R is equal to e raised to ln R is equal to R, showing that phi is on to R plus. Step 4. Verifying the homomorphism property. For xy belongs to R, we have phi of x plus y is equal to e raised to x plus y, which is equal to e raised to x into e raised to y, which is equal to phi of x, phi of y. Thus, phi is an isomorphism between R plus and R plus dot, and hence are isomorphic to R plus. Example 2. Consider the following two binary structures. A. U is equal to set for Z belongs to C such that mod Z is equal to 1 with the ordinary multiplication, and B. For C belongs to R plus, RC is equal to set theta belongs to R such that 0 less than or is equal to theta less than C with the operation addition modulo C defined by for theta 1, theta 2 belongs to RC. Theta 1 plus theta 2 is equal to set theta 1 plus theta 2 if theta 1 plus theta 2 less than C, or theta 1 plus theta 2 minus C if theta 1 plus theta 2 greater than or is equal to C. Show that the above two binary structures are isomorphic. Give a geometric interpretation. Solution. Step 1. Consider phi from RC to U defined by phi of theta is equal to e raised to I 2 pi theta by C, which is equal to cos 2 pi theta by C plus I sin 2 pi theta by C. Step 2. Phi is 1 to 1. Phi of theta 1 is equal to phi of theta 2 implies e raised to I 2 pi theta 1 by C is equal to e raised to I pi theta 2 by C, which implies 2 pi theta 1 by C is equal to 2 pi theta 2 by C, as the exponential function is 1 to 1, which implies theta 1 is equal to theta 2. Step 3. Phi is onto. We note that the given U is a circle in the Euclidean plane with center at the origin and radius 1. As shown in figure 1, corresponding to any set in U, there is a unique theta in R such that 0 less than or is equal to theta less than 2 pi and z is equal to e raised to I theta. Take theta C is equal to C by 2 pi into theta. Then 0 less than or is equal to theta C less than C, and phi of theta C is equal to e raised to I 2 pi theta C by C, which is equal to e raised to I 2 pi by C into C by 2 pi theta, which is equal to e raised to I theta, which is equal to Z. Hence, phi is onto. Step 4. Phi satisfies homomorphism property because phi of theta 1 plus theta 2 is equal to e raised to I 2 pi theta 1 plus theta 2 by C, which is equal to e raised to I 2 pi theta 1 by C into e raised to I 2 pi theta 2 by C, which is equal to phi of theta 1 into phi of theta 2. Hence, phi is an isomorphism between the given two binary structers and hence they are isomorphic. Geometrically speaking, the unit circle and the left closed and right open interval 0C are structurally the same. Example 3. Let n be a positive integer and let un be the set of the nth roots of unity in C with the binary operation usual multiplication of complex numbers. Also, addition modulo n is a binary operation on Zn, which is equal to set consisting of 0, 1, 2, etc. n minus 1. Show that the binary structures un dot and Zn addition modulo n are isomorphic. Solution. Recall that for a given positive integer n, the nth roots of unity are given by cos 2 pi r by n plus I sin 2 pi r by n, where r is equal to 0, 1, 2, etc. n minus 1. Now define phi from Zn to un as follows. For r belong to Zn, phi of r is equal to cos 2 pi r by n plus I sin 2 pi r by n. It can be verified that phi is 1 to 1 and onto. Also, phi of r1 addition modulo n r2 is equal to cos 2 pi r1 addition modulo n r2 by n plus I sin 2 pi r1 addition modulo n r2 by n, which is equal to e raised to I 2 pi by n r1 addition modulo n r2, which is equal to e raised to I 2 pi by n r1 plus r2 if r1 plus r2 less than n, or e raised to I 2 pi by n r1 plus r2 minus n if r1 plus r2 greater than or is equal to n, which is equal to e raised to I 2 pi by n r1 into e raised to I 2 pi by n r2 if r1 plus r2 less than n, or e raised to I 2 pi by n r1 into e raised to I 2 pi by n r2 into e raised to I minus I 2 pi if r1 plus r2 greater than or is equal to n, which is equal to e raised to I 2 pi by n r1 into e raised to I 2 pi by n r2, since e raised to minus I 2 pi is equal to 1, which is equal to phi of r1 into phi of r2. Hence, Phi is an isomorphism between the given two binary structures and hence they are isomorphic. Example 4. Show that the binary structures Z4 addition modulo 4 is isomorphic to U4 dot. Solution. This can be treated as a special case of the previous example, but we give details. Note that Z4 is equal to set 0, 1, 2, 3. Consider the map phi from Z4 to U4 defined by phi of 0 is equal to 1, phi of 1 is equal to I, phi of 2 is equal to minus 1, phi of 3 is equal to minus I. Clearly, phi is 1 to 1 and onto. Also, phi of A addition modulo 4B is equal to phi of A into phi of B for every AB belongs to Z4. In particular, phi of 2 addition modulo 4 3 is equal to phi of 1 is equal to I and phi of 2 phi of 3 is equal to minus 1 into minus I which is equal to I. Therefore, phi of 2 addition modulo 4 3 is equal to phi of 2 into phi of 3. Example 5. Consider the following two binary structures. A. Set the set of integers with ordinary addition and B. 2z is equal to set consisting of 2n such that n belongs to set, the set of even integers with ordinary addition. Show that the above two binary structures are isomorphic. Solution. Step 1. Consider phi from set to 2z defined by phi of n is equal to 2n for n belongs to set. Step 2. Phi is 1 to 1 because phi of m is equal to phi of n implies 2m is equal to 2n implies m is equal to n. Step 3. Phi is onto. If n belongs to 2z, then n is even. So, n is equal to 2m for m is equal to n by 2 belongs to set. Hence, phi of m is equal to 2 into n by 2 which is equal to n. So, phi is onto. Step 4. Phi satisfies homomorphism property because phi of m plus n is equal to 2 into m plus n which is equal to 2m plus 2n which is equal to phi of m plus phi of n. Hence, phi is an isomorphism between the given two binary structures and hence they are isomorphic. Example 6. Show that Z under addition is not isomorphic to R under addition. Solution. Z is a countable set and R is an uncountable set and hence it is not possible to find a one-to-one and onto function between them. Hence, Z under addition is not isomorphic to R under addition. Structural property of a binary structure. In example 6, we have shown that given binary structures are not isomorphic by saying that there is no one-to-one and onto map between the underlying sets. Sometimes there may be one-to-one and onto maps between the binary structures, but still they need not be isomorphic. In that case, we usually show that the binary structures are not isomorphic. If this is the case, by showing that one binary structure has some structural property that the other does not possess. A structural property of a binary structure is one that must be shared by any isomorphic structure. It is not concerned with names or some other non-structural characteristics of the elements. The following are examples of some structural properties and some non-structural properties of groups. Possible structural properties. The operation is commutative. The set has 8 elements. X star x is equal to x for all x belongs to S. The equations A star x is equal to B has a solution x in S for all A B belongs to S. Possible non-structural properties. The operation is called composition. The group contains 3. All elements of the group are numbers. The elements of the group are matrices. The given set is a subset of C. Example 7. We cannot say that Z and 2Z under addition are not isomorphic because phi belongs to Z and phi not an element of 2Z. These are not structural properties but rather have to do with just the names of the elements. Actually, Z and 2Z are isomorphic. it can be verified that the map phi from Z to 2Z defined by phi of n is equal to 2n is an isomorphism. Example 8. R star, the set of non-zero real numbers, is not isomorphic to C star, the set of non-zero complex numbers, when both are considered binary structures under usual multiplication. Solution. The argument is this. The equation x square is equal to a has a solution x in C star for every a in C star, but x square is equal to minus 1 has no solution in R star. Hence, there is no phi from C star to R star exists such that phi of xy is equal to phi of x into phi of y for xy belongs to C star. Example 9. Q star, the set of non-zero rational numbers, is not isomorphic to R star, the set of non-zero real numbers, when both are considered binary structures under multiplication. Argument 1. There is no one-to-one and on-to correspondence between them, as Q star is countable while R star is uncountable. Argument 2. Every element in R star is the cube of some element of R star. That is, for A belongs to R star, the equation x cube is equal to A has a solution in R star. That is not true for Q star. For example, x cube is equal to 2 has no solution in Q star. Example 10. The group R star of non-zero real numbers under multiplication is not isomorphic to the group R of real numbers under addition. Argument. An equation x plus x is equal to a always has a solution in R plus for every a in R. But the corresponding equation x dot x is equal to a does not always have a solution in R star dot. For example, if a is equal to minus 1. More explanation. If there is an isomorphism phi from R to R star exists, then for x plus x is equal to a in R, we have phi of a is equal to phi of x plus x is equal to phi of x into phi of x, as we are assuming that phi satisfies homomorphism property, which is equal to phi of x square in R star. That is, phi of x belongs to R star with phi of x square is equal to phi of a. Equation number 3. Now take phi of a is equal to minus 1. This is possible since phi is onto. Then equation 3 gives a contradiction to the above noted fact that y square is equal to minus 1 has no solution in R star. Example 11. The binary structure M2R dot of 2 by 2 real matrices with the usual matrix multiplication is not isomorphic to R dot with the usual multiplication. Since multiplication of real numbers is commutative, but multiplication of matrices is not commutative. Definition. Let S star be a binary structure. An element E in S is an identity element for star if E star S is equal to S star E is equal to S for all S in S. Fundamental results. Theorem 1. Uniqueness of identity element. A binary structure S star has at most one identity element. That is, if there is an identity element, it is unique. Proof. To show the uniqueness of identity, we use the standard method of assuming that we have two elements E and E1 such that E star S is equal to S star E is equal to S and E1 star S is equal to S star E1 is equal to S for every S in S. Claim. E1 is equal to E. Consider the product E star E1. Regarding E as the identity, E star E1 is equal to E1, equation number 4. Regarding E1 as the identity, E star E1 is equal to E, equation number 5. LHS of 4 and 5 are the same and hence E1 is equal to E, showing that identity of a group is unique. Theorem 2. Suppose S star has an identity element E 4 star. If phi from S to S dash is an isomorphism of S star with S dash star dash, then phi of E is an identity element for the binary operation star dash on S dash. Proof. We first note that to show that phi of E is an identity element for the binary operation star dash on S dash, it is enough to show that phi of E star dash S dash is equal to S dash star dash phi of E, which is equal to S dash for every S dash in S dash. To prove this, let S dash belongs to S dash. Because phi is an isomorphism, it is a one-to-one map of S onto S dash. In particular, correspondence to the given S dash in S dash, there exists S in S such that phi of S is equal to S dash. Now, E is an identity element for star, so that E star S is equal to S star E is equal to S. Because phi is a function, each element has a unique image, and hence the same element E star S is equal to S star E is equal to S has a unique image given by phi of E star S is equal to phi of S star E is equal to phi of S. Using the homomorphism property of the isomorphism phi, the above becomes phi of E star dash phi of S is equal to phi of S star dash phi of E, which is equal to phi of S. As phi of S is equal to S dash, the above gives phi of E star dash S dash is equal to S dash star dash phi of E is equal to S dash. Since S dash belongs to S dash is arbitrary, the above gives phi of E star dash S dash is equal to S dash star dash phi of E is equal to S dash for every S dash in S dash as desired. Group isomorphism. We now discuss isomorphism between two groups which are particular binary structures. Definition. A function phi from a group G onto a group G dash is a group isomorphism if phi is 1 to 1, phi is on to, and phi of x star y is equal to phi of x star dash phi of y for all x y belongs to G. Equation number 6. Definition. Isomorphous group. Two groups G and G dash are said to be isomorphic if there exists an isomorphism phi from the group G onto the group G dash. Notation. We denote two groups G and G dash are isomorphic as follows. In the session Properties of Groups and Subgroups, we will see the stronger form of Theorem 1 as follows. Theorem 1a. Existence and uniqueness of identity. In a group G with binary operation star, there is only one identity E such that E star x is equal to x star E is equal to x for every x in G. In view of Theorem 1a, a group has exactly one identity element and we refer it the identity element in the group. Now, Theorem 2 discussed so far in this session can be restated in group theory as follows. Theorem 2a. Suppose E is the identity element in the group G star if phi from G to G dash is an isomorphism of G star with the group G dash star dash, then phi of E is the identity element in G dash. We now discuss some more fundamental results in connection with isomorphic group. Theorem 3. Let phi from G to G dash is an isomorphism of G with G dash. If A belongs to G, then phi of A inverse is equal to phi of A inverse. Proof. We want to show that phi of A inverse is equal to phi of A inverse. That is, we want to show that the inverse of phi of A in G dash is phi of A inverse. For this, we want to show that phi of A inverse into phi of A is equal to phi of E is equal to phi of A into phi of A inverse. Since by 1 we know that the identity element in G dash is E dash is equal to phi of E. For A belongs to G, we have phi of E is equal to phi of A inverse A, which is equal to phi of A inverse into phi of A. Likewise, phi of E is equal to phi of A inverse is equal to phi of A into phi of A inverse. Thus, for every A in G, we have phi of A inverse into phi of A is equal to phi of E, which is equal to phi of A into phi of A inverse. showing that inverse of phi of A is phi of A inverse. That is, phi of A inverse is equal to phi of A inverse for every A in G. Theorem 4. Any infinite cyclic group G is isomorphic to the group Z of integers under addition. Proof. Since G is cyclic, it has a generator, say A. Use multiplicative notation for the operation in G. Thus, G is equal to set A raised to n such that n belongs to Z. In other words, each element in G has the form A raised to n for some n belongs to Z. It can be shown that the elements A raised to n of G are all distinct. That is, A raised to n not is equal to A raised to m if n not is equal to m. Step 1. Define phi from G to Z by phi of A raised to n is equal to n for every A raised to n belongs to G. Step 2. Phi of A raised to n is equal to phi of A raised to m implies n is equal to m implies A raised to n is equal to A raised to m. Thus, phi is 1 to 1. Step 3. For any n belongs to Z, the element A raised to n belongs to G is mapped onto n by phi. Thus, phi is onto Z. Step 4. Now, phi of A raised to n A raised to m is equal to phi of A raised to n plus m, which is equal to n plus m. Equation number 7. Note that the binary operation in 7 was in the group G. Also, phi of A raised to n plus phi of A raised to m is equal to n plus m. Equation number 8. Note that the binary operation plus in 8 was in the group Z and is the usual addition. From 1 and 2, we have phi of A raised to n into A raised to m is equal to phi of A raised to n plus phi of A raised to m. Hence, phi is an isomorphism between G and Z, and hence G isomorphic to Z. Theorem 5. Let G be a collection of groups and define G isomorphic to G dash for G and G dash in G if there exists an isomorphism phi from G to G dash. Then isomorphism is an equivalence relation. Proof. Reflexive. G isomorphic to G. It can be verified that the function I from G to G where I of G is equal to G for every G in G is an isomorphism. Details are left as an exercise between G and G and hence G isomorphic to G. Symmetric. If G isomorphic to G dash, then G dash isomorphic to G. It can be verified that if phi from G to G dash is an isomorphism, then phi inverse from G dash to G is an isomorphism. Therefore, if G isomorphic to G dash, then G dash isomorphic to G. Transitive. If G isomorphic to G dash and G dash isomorphic to G double dash, then G isomorphic to G double dash. It can be verified that if phi from G to G dash and gamma from G dash to G double dash are isomorphism, then gamma phi from G to G double dash is also an isomorphism. If G isomorphic to G dash isomorphic to G double dash, then G isomorphic to G double dash. Remark. By theorem 5, isomorphism is an equivalent relation and hence it partitions the collection of all groups G in such a way that any two groups in the same equivalent class or cell are isomorphic and groups in different equivalent classes or cells are not isomorphic. Example 12. We know that any group of order 1 contains only the identity element and hence any two groups of order 1 are isomorphic. We say this as there is only one group of order 1 up to isomorphism. Similarly, any two groups of order 2 are isomorphic and we say this as there is only one group of order 2 up to isomorphism. It can be seen that any two groups of order 3 are isomorphic and we say this as there is only one group of order 3 up to isomorphism. There are exactly two different groups of order 4 up to isomorphism and they are the group Z4 and the clean 4 group V. By the word up to isomorphism, we mean that any group of order 4 is isomorphic either to Z4 or to V, but not both. How to show that groups are not isomorphic? We turn now to the reverse question, namely, how do we demonstrate that two groups G and G dash are not isomorphic if this is the case? This would mean that there is no one-to-one function phi from G onto G dash with the property phi of xy is equal to phi of x into phi of y. In general, it is clearly not feasible to try every possible one-to-one function to find out whether it has the above property, except in the case where there are no one-to-one functions. This is the case. For example, if G and G dash are of finite order and have different numbers of elements. Example 13. Z4 and S3 are not isomorphic since Z4 has 4 elements and S3 have 6 elements. It is not be possible to find a one-to-one function between Z4 and S3. Example 14. Z under addition is not isomorphic to R under addition, for there is no one-to-one function from Z onto R. Note, Z is a countable set and R is an uncountable set, and hence it is not possible to find a one-to-one and onto function between them. Example 15. Z4 is not isomorphic to the clean 4 group V, since former is cyclic while the latter is not. Example 16. We cannot say that Z and 3Z under addition are not isomorphic because 17 belongs to Z and 17 not an element of 3Z. These are not structural properties but rather have to do with just the names of the elements. Actually, Z and 3Z are isomorphic. It can be seen that the map phi from Z to 3Z defined by phi of n is equal to 3n is an isomorphism. Example 17. We cannot say that Z and Q both under addition are not isomorphic because 1 by 2 belongs to Q and 1 by 2 not an element of Z. But we can say that Z and Q are not isomorphic because Z is cyclic and Q is not. Example 18. The group Q star of non-zero elements of Q under multiplication is not isomorphic to the group R star of non-zero elements of R under multiplication. Argument 1. There is no one-to-one and onto correspondence between them, as Q star is countable while R star is not. Argument 2. Every element in R star is the cube of some element of R star. That is, for every A in R star, the equation x cube is equal to A has a solution in R star. This is not true for Q star. For example, x cube is equal to 2 has no solution in Q star. In this session, first we have discussed isomorphism between binary algebraic structures and the method to find how algebraic structures are isomorphic or not. Then we extended these ideas to group theory, which is our main interest. Before moving to the next unit, let us try to answer these questions. Partition the following collection of binary structures into sub-collection of isomorphic structures. Here, superscript star means all non-zero elements of the set. 2Z under usual addition, Z under usual addition, Z5 under addition modulo 5, R star under usual multiplication, Z4 under addition modulo 4, R plus under usual multiplication, Q star under usual multiplication, 13Z under usual addition, C star under multiplication, 6Z under usual addition, R under usual addition, Q under usual addition. Give two arguments showing that Z4 is not isomorphic to the clean 4 group V. Give a formal proof of the statement that if phi is an isomorphism of a group G with a group G dash and H is a subgroup of G, then phi of H is equal to set phi of H such that H belongs to H is a subgroup of G dash. Hope you enjoyed these sessions. See you next time. Till then, take care.